The next theorem is going to involve extensions of functions in the spirit of the example that I already discussed previously, right? We looked at the function x squared on an open interval from 0 to 1, or from -1 to 1, I don't remember. We could not apply a theorem that a continuous function about continuous functions on closed and bounded intervals because interval was not closed. But we saw that we could consider a function on a closed interval from 0 to 1 where it is uniformly continuous, therefore it becomes uniformly continuous on an open version of the interval. So now we can formulate this as a separate theorem. So a theorem a function f on the open interval AB, principal can be half open, is uniformly continuous if and only if it can be continuously extended, or I'll just use this different wording here. If it can be extended to a continuous function f tilde on a closed interval from A to B. Now, let me give you a definition first. Definition. F tilde defined on some set J is an extension of f defined on some interval I with I being a subset of J if f tilde of x is equal to f of x for any x in I, right? So what does it mean? I have two, let's say, intervals I and j. J is a larger interval. I have my function defined on an interval I, my function f of x. And then I have another function which is defined on a larger interval j. And then as long as f tilde and f coincide on the interval I, then I will call f tilde an extension of f to the interval j. And so in our theorem, we're saying that if there exists an extension of our function f, which is continuous on a closed interval from A to B, then f must be uniformly continuous on an open version of AB. So let's do the proof. Let's first go in the opposite direction. So suppose that f can be extended to a continuous f tilde on closed interval from A to B. Well, if f tilde is defined on a closed interval from A to B, then f tilde is uniformly, and that's the result of a theorem, is uniformly continuous on AB, right? Because any function which is continuous on a closed and bounded interval is uniformly continuous. But if f is uniformly continuous on AB, then clearly it is uniformly continuous on any smaller interval. So in particular, it's uniformly continuous on an open interval from A to B. But f tilde and f are exactly the same on the open version of AB, and so f is trivially uniformly continuous on AB. So this direction is easy. Let's do the opposite. Let's suppose that f is uniformly continuous on an open interval from A to B, and then what do we need to do? We need to show find f tilde defined, in fact, f tilde continuous on the closed interval from A to B, such that f of x is equal to f tilde of x for all x inside the open interval AB. Okay, so then I already know what f tilde is inside the open interval AB. I just need to be able to define it at the endpoints. So therefore, only need to define f tilde at A and at B, right? So I have my function f, and I want to define it at two additional endpoints of the interval in such a way that the resulting function is going to be continuous on a closed interval. Let's work with A only, because with B it will be the same thing. So we're going to construct the extension at A. All right, so how we're going to do that? Let's do the following. Let us do the following. So we want to construct an extension in such a way that it is going to be continuous, right? What does it mean that the extended function will be continuous? It means that if, okay, so let's actually write this down. We want the extension to be continuous at A, right? What does it mean? It means that what we want, if limit n goes to a, we're sitting inside the interval from a to b, so we're going to a from the left. Limit as, well, what am I doing here? So limit as n goes to infinity of xn is equal to a, and all xn are contained in the interval from a to b, then the limit n goes to infinity of f tilde of xn, I want that to be f tilde of a, right? That's what it means for the function to be continuous at a. If I take any sequence of x's that goes to a, then f tilde of xn must be f tilde of a. All right, so that's fine. So that's how I want, that's a property that I want my extension to satisfy. One thing that I want you to understand is that if I want to extend the function just to the endpoints, what I need to do, I simply need to define values of the function at the endpoint. So in principle, I could just say that f tilde of a is equal to 7, or f tilde is equal to 20. That will define a function f tilde. But 7 or 20 are not necessarily good, because f tilde defined this way is not necessarily going to be continuous. So there should be infinitely many ways to extend a function to a closed interval from an open interval. But only one of those is going to give me a continuous function. And that's the one that I want to determine. All right, so fine, that's what I want. Or what is f tilde of xn? So xn is a sequence inside the open interval AB. And inside the open interval AB, I know that f tilde and f are the same thing. So what I want is that the limit as n goes to infinity of f of xn, that is going to be my f tilde of a. Right, so I can define f tilde of a in this way. Well, but there is a problem here. I don't know in advance. So I chose one sequence, xn, that goes to a, right? I take a limit of f of xn as n goes to infinity. I get a number. I call that number f tilde of a. The problem is that if I choose, I don't know a priori that my function is going to be continuous at a. So if I choose a different sequence of xn, that goes to a, it's entirely possible that the limit of f of xn for that sequence is not going to give me the same number. So I cannot be sure that f tilde is well defined. In fact, I'm not even sure at this point if a sequence f of xn will actually converge or not. So what I need to do is, first, I need to prove, first, need to prove that the limit n goes to infinity of xn, that this thing exists. Then use that number to define f tilde of a. And then number two, I need to show that this number is independent of the sequence that I'm using. I need to show that for any two sequences. Let's say xn1, in AB, and xn2 in AB, such that the limit as n goes to infinity of xn1 equal to the limit n goes to infinity of x and 2. If both of these are equal to a, then the limit n goes to infinity f of xn1 is the same as the limit n goes to infinity f of xn2. Right? So if the second part is true, then it means that it doesn't matter which sequence I chose originally to define f tilde of a, I would always have the same number, so it really doesn't matter which sequence I used. Okay, so let's prove 1. Okay, let's choose again any sequence xn in AB such that limit n goes to infinity f of xn, well, not f of xn yet, of xn is equal to a. Okay, so xn is inside the interval AB. We know that our function f is uniformly continuous. Then because f is uniformly continuous on AB, and by using the theorem, well, actually before that, sorry. Before I do this, xn goes to a, that is a convergent sequence, so xn is a Cauchy sequence. And now, because f is uniformly continuous by a theorem, we have that f of xn is uniformly continuous. Hey. Because xn is Cauchy, f of xn is Cauchy. Sorry. And if f of xn is Cauchy, then f of xn is a convergent sequence. So it converges to a real number. And I'm going to denote this number by f tilde of a, right? So this allows us to define what f tilde of a is, right? It's just a limit. I take any Cauchy sequence, any sequence which converges to a, then f of xn, which I just showed, is also a convergent sequence. It converges to something, so we call that number f tilde of a. So that's our definition of f tilde of a. And now proof 2, part 2. I'm going to use slightly different notation than above. Suppose that maybe Sn is another sequence such that the limit n goes to infinity of Sn is equal to A. Okay, so fine, we have a sequence like that. So it's equal to A. Well, so then I can consider a new sequence which I'm going to construct in the following way. I'm just going to interleave x's and s's. x1, s1, x2, s2, etc. Right, so x's go to A, s's go to A. So then clearly it should be easy to show that this sequence, let's give this sequence a name. Let's call it Tn. So then it's clear that the limit n goes to infinity of Tn must be equal to A, because individually both xn and Sn go to A. All right, fine. So, but then, if we use the same idea as in the part 1, we have that f of Tn, f of Tn is a convergent sequence, right? Using the same ideology. Tn is a convergent sequence, so it must be a Cauchy sequence, so therefore, because of a uniform continuity of f, f of Tn is a Cauchy sequence, so therefore it converges. So f of Tn is a convergent sequence. Right, so let's suppose that limit as n goes to infinity of f of Tn, that this is equal to some number, I don't know, let's call it p, right? Well, but then my sequence xn is a subsequence of Tn, right, by construction. All x's are in order in Tn, interleaved with Sn. So if xn is a subsequence of Tn, then f of xn is a subsequence of f of Tn. And so therefore the limit n goes to infinity, f of xn must be the same as a limit of as n goes to infinity of Tn, right? Because the limit of a subsequence must be the same as the limit of the original sequence. So this is equal to p. But I already know that the limit of f of xn is a thing that I called f tilde of a. So therefore, from this we conclude that p is equal to f tilde of a, because limit n goes to infinity f of xn is equal to f tilde of a. Well, but then if I look at the limit of f of Sn, right, Sn is also a subsequence of Tn. So f of Sn would be a subsequence of f of Tn. So it must converge also to the same number. So we prove that P is equal to f tilde of A. And further, and maybe let me copy some of the stuff from here. So the same is true about Sn, as I said. Sn is also a subsequence of Tn. So therefore, f of Sn is a subsequence of f of Tn. And so therefore, the limit f of Sn is also equal to P, which is, as we just showed, is equal to f tilde of alpha, f tilde of A. And so that means that we're done, because it means that if I take any sequence that goes to A, any sequence of x's that goes to A, this proves that the limit of f of that sequence must be f tilde of A, which means that f tilde is continuous at A by the sequential definition of continuity. Okay, so, and we already used this theorem before on the example of x squared and open interval, so that's how you use it. And I'm going to conclude this section with one additional theorem, which I'm going to state, but not prove now. We're going to prove it later on, once we learned about the derivative. So theorem is just a good test for checking if the function is uniformly continuous or not. Suppose not if it is not uniformly continuous, but to check if the function is uniformly continuous. Suppose that f is differentiable on the interval I, and f prime of x is less than some number m for all x and I. In other words, function f has a bounded derivative on your interval I. Then f is uniformly continuous on I. And I'm just going to do one example of that. Let's think about this. Okay, so example is f of x equal to radical of x uniformly continuous on the interval from 1 to infinity. So what do we think? Well, so because I'm giving this example after the theorem, after this theorem about differentiability, then probably this theorem has to be used here. But before using it, let me point out one thing, that square root of x is definitely continuous everywhere in its domain. So in particular, it is continuous on the interval from 1 to infinity. but that is of little help to us because, again, a continuous function in a closed interval is uniformly continuous only if the interval is bounded. And in this case, it's not bounded. So let's see how the differentiability is going to help us. Let's take f prime of x. That's derivative of x to the 1/2, so 1/2 x to the minus 1/2 or 1 over 2 square root of x. Well, so that's a positive number, right? And of course, it's less or equal than 1/2 on the interval from 1 to infinity. So then, the conclusion, by the theorem that we just proved, f is uniformly continuous on the interval from 1 to infinity. And we can actually combine this example with what we have done before, right? We already showed that square root of x is uniformly continuous on the interval from 0 to 1. And if it is uniformly continuous from 0 to 1 and uniformly continuous on the interval from 1 to infinity, then it's easy to see that actually radical of x should be uniformly continuous on the entire interval from 0 to infinity.